Hello friends, in this video we are going to discuss about subspace. A subspace is nothing but just an extension of a subset if I say. So let us first discuss what is a subset. We say that the set A is a subset of set B if every element of A is there inside the set B, correct? If we extend this idea, then there comes something known as a subspace. Suppose my W is a non-empty subset of a vector space V. I have some vector space. Inside that vector space V, I have a non-empty subset W, and this W will be called as the subspace of V if this W is a vector space under the operation of V. That means what? Whatever operation was there defined on V, if by using those two operations you are able to prove that non-empty subset W is a vector space, then that W becomes a subspace, or you can say vector subspace of V. Okay. So in short or in general, if I try to say what is the meaning of a subspace, it is nothing but like inside a bigger vector space there is a smaller vector space that will be called as a subspace. Okay. So given any vector space, any non-empty subset of it is said to be a vector subspace if it is itself a vector space under the operation of V. Now we know that if I want to check any given non-empty set is a vector space, I need to check those 10 conditions, 5 under addition and 5 under the scalar product. But when we talk about a subspace, whenever I want to check a given non-empty subset is a subspace or not, there are some easy tricks that we can apply, or the easy theorem which helps us to check whether the given non-empty subset is a subspace or not. There is one which is a stronger version which we will discuss, and the two weaker version I will give the statement to you. The proof can be done in the similar pattern. Okay, let us try to do that theorem. Okay, we know that W is a non-empty subset of a vector space V, then W is a subspace of V if and only if your alpha W1 bar plus W2 bar is an element of W for all alpha inside R and for all W1 bar comma W2 bar inside W. So the definition of a vector space can be this. What we said, it is a subspace if and only if it is a vector space under that operation. And over here this theorem is telling us to check, we are not necessary to check those 10 conditions. If we just satisfy this single condition, then it is enough that is going to be a subspace. We will see how this single statement can overcome those 10 conditions or the extra 9 conditions. Let's just prove this. Suppose my W is a subspace of V. We will go in this way. This is an if and only if theorem. That means we are going to prove both the ways. Suppose I assume that my W is subspace of V. I want to prove this. I want to prove alpha W1 bar plus W2 bar is an element of W for all alpha inside R, for all W1 bar, W2 bar inside W. Okay, I want to prove this. Now we know that if it is a subspace, then it satisfies 10 conditions, because subspace means what? It is itself a vector space, and every vector space satisfies those 10 conditions. Okay. So I know it satisfies. That means if I consider for any element alpha inside R, and I consider any element W1 bar inside W, then my alpha into W1 bar is an element of W. By which condition? By M1, right? We know that scalar product is binary or closed. Right? So I know alpha W1 bar is an element of W for all alpha inside R and for all W1 bar inside W. Now I know that if I add this with any other element, still I will be inside W. By which condition? By M1, correct? By A1, correct? By A1. By A1 condition we know that the addition that we define is closed. Hence if I add this, still I am inside W. And this is true for all alpha inside R, for all W1 bar comma W2 bar inside W. So the one way is clear, and actually it is trivial. if my given subset, given non-empty subset is a subspace, then it satisfies that condition. But the other way around, that means if this condition is satisfied, I want to prove that is a subspace of V. Okay, just going in the converse manner is interesting. This was actually a trivial part. Let us see the converse. I want to show that W is a subspace of V. That means I want to show that my W is a vector space under the operation of V. Any given set is a vector space if it is non-empty, operations are defined and satisfy 10 conditions. We know that it is non-empty set. Also the operation on W are defined, which are the operation of V. So we have defined the operation. Now it is time to check those 10 conditions. Okay. So the first condition, A1. What was A1? It was about binary. So if I consider any two element, W1 bar plus W2 bar, if I consider any two element, that if I add them, will it be inside it? Make sure you know that this condition is true now. For the converse case, this is true. So you know that alpha W1 bar plus W2 bar is an element of W for all alpha inside W, for all W1 bar, W2 bar inside W. So in that condition, we take alpha is equal to 1 and we get this. By the properties we know that 1 into W1 bar is same as W1 bar. Correct? Hence by taking alpha is equal to 1, we see that the first condition is satisfied. Correct? Let us see the second condition. That is to show that W1 bar plus W2 bar plus W3 bar is same as W1 bar, W2 bar plus W3 bar. Correct? This is nothing but the associativity. This should be true for all W1 bar, W3 bar inside W. Can someone tell me how this is going to be true? Because in the given statement that we have, we don't know this condition is true. But something better than this we know. What we know that our V is a vector space. Hence, every element of V satisfies those conditions. Every element of W is an element of V because it is non-empty subset. Hence, I know that this W1, W2, W3 is an element of V. Hence, it satisfies all the conditions. Hence, it satisfies this A2 also. So, we can say that this associativity is nothing but inherited from V. W is getting the associativity in the inheritance from the V. We can use that word, right? Okay. So, second condition is also satisfied since every element of W is inside V. It will satisfy associativity. The third condition. Okay. Third condition is interesting. We know that our W is non-empty set. Correct? We know that W is non-empty set. Then what happens if the set is non-empty? There exists some element. W bar inside W. There will exist some element that is non-empty. Now what I consider, I know that on the place of alpha, I will choose -1. On the place of W1, I will choose W bar. On the place of W2, I will choose again W bar. Correct? Since I know this is true for every element of R and every element of W, I can write this. Can you tell me what is this? By the properties, we know that this is nothing but the additive inverse of this. Hence, I know that my 0 bar is an element of W. Okay, I can write 0V if you want. Correct? We are using the property. Properties tells us if you take a scalar product with -1, you get the additive inverse. If I adding the additive inverse, then I should get the identity element. So we know that the 0 bar is an element of W. So the most of the proof will be done by this manner. We will choose some element for alpha, W1 and W2. Okay. So we know that alpha A3 is true. Now let us go for A4. What was A4? It is about the inverse. We want to prove that for every element the inverse exists inside it. A4. For any element W bar inside W, I want to prove that -W bar is also an element of it. Okay. So we take what? We take alpha is equal to -1. We take W1 bar is equal to W bar. W2 bar is equal to 0 bar. Can I take this as a 0 bar? Yes, we can. Since we just now proved 0 bar is an element of W, hence we can take. Then what does this becomes? This becomes minus 1 W bar plus W2 bar is same as 0 bar and it is an element of W. Hence we know that minus W bar is an element of W. So for every element there exists an additive inverse inside it. The fourth one is what? The fifth one is nothing but the commutativity. If every element of V commute, then every element of W will also commute. Correct? Hence we can say that this A phi is also inherited from V. Okay, if you want to write, you can write it like this. Is equal to W2 bar plus W1 bar for all W1 bar comma W2 bar inside W, since it is subset of V. Correct? So this is also one of the property which is getting inherited. Okay, let us see the M1 condition. M1 condition tells us that the scalar product is binary. Okay, so my M1, that is the thing, but what we will do, we will take W2 bar is equal to 0 bar. What we get is alpha W1 bar is an element of W for all alpha inside R and for all W1 inside W. So this is nothing but the scalar product is closed inside W. Okay. You can observe that M2, M3 or even your M4 or M5, all those four conditions will get inherited from V. What was M2? M2 was telling us splitting or distribution of a vector over scalar, then distribution of scalar over vector, then we have associativity, then we have 1 times W1 bar is equal to W1 bar. All these conditions are true for every element of V, correct? And every element of W is inside V. Hence we can say that every element of W will satisfy those four conditions. So we observe that only 3 of the conditions, that means binary under addition, binary under scalar product, and existence of 0. These are the 3 conditions. If any set has, any non-empty subset has, then it becomes a vector space. Because we just observe other conditions are getting inherited from V. Correct? So this way you can say that given any non-empty subset is a subspace if and only if it satisfies this condition. Okay? So this way we can prove given any non-empty subset is a vector space. There are 2 other ways which is nothing but just an extension of this. Okay, let us see that. I hope you can write the rest of the part. Let us observe this. What kind of the simple changes that can be made under this? Okay, the changes that we can make, the second theorem which is just an extension of this. You might find in some reference book, they will use like this. They will increase one beta over here and write the condition like this. They will tell you W is a subspace of V if and only if this condition is satisfied. Correct? So actually what the theorem that we did is just the strongest version that gives you the answer in the shortest steps. This required one more steps I think, but it is fine. This also you can find in some reference book. So W is a subspace of V if and only if alpha W1 bar plus beta W2 bar is an element of W for all alpha beta inside R for all W1 bar W2 bar inside W. Okay. The last one, which is the weakest form I will say, but it is also good to check. Okay. What we say is W is a subspace of V if and only if it satisfies 3 conditions. The first condition is the 0 must be an element of W. The second is W1 bar plus W2 bar must be an element of W for all W1 bar comma W2 bar element of W. The third one is alpha W1 bar is an element of W for all alpha inside R and for all W1 bar inside W. So this is nothing but the third theorem of the same kind. So all the 3 theorems doing same thing, checking whether the given non-empty subset is a subspace or not. Over here it is getting more clear that only 3 conditions are enough. That is 0, addition is closed and scalar product is closed. other things are getting inherited from V being a vector space. Okay, so this way you can prove any given non-empty set is a subspace. So I think it is enough for this class. In the next class we will discussing some example of subspace. Thank you for watching the video. If you are new to my channel, please subscribe, share it with your friends.